So welcome to section 11.9, being broadcast live from my basement bunker. We're going to go over representing functions as power series. You might remember power series from the last section. They look like this. This one, of course, is centered at 0. This one is centered at some point A. But both of them are power series. And what we're going to work on in this section is figuring out an expression for C sub n so that these actually converge to specific series. Now, you might remember something like this. This is a geometric series. To get from one term to the next, you multiply by x. The sum of a geometric series is a sub 1 divided by 1 minus r, like that. Now, a sub 1 in this case is actually 1. And the ratio, the common ratio that you multiply to get from one term to the next is x. So the sum of this, which can be written as this in series notation, is 1 over 1 minus x. And that's going to be really handy. We're going to use that a lot. Now quiz yourself. When does this converge? For what values of x? If you said absolute value of x is less than 1, bingo. Bonus credit for you. But what if you have something a little bit different in your series or your function, and you still wanted to write it as a series? So let's do a few examples, actually more than a few. We'll start with this one. F of x is 2 over 3 minus x. Now, if I want to use this idea here, and this function and this series, I got to make this look like that. So there's a few things I'm going to work on. I guess one of them is I'll factor the 2 out in front, leave behind 1 over 3 minus x. Of course, that 2 multiplies this expression, and that's fine. But in order to make it look more like that, in fact, almost exactly like that, I need a 1 in this first position in the denominator. So that would mean I'd have to divide this by 3. Well, I can't just divide that by 3 because I want to. But what I can do is multiply by 1/3 in the numerator and 1/3 in the denominator. So, okay, let's do that. That gives me 2 times 1/3 over 1 minus x over 3. Now the 2 times 1/3, I can bring that together and write that as 2/3 times 1 over 1 minus x over 3. That's exactly what I wanted. I wanted something in this form right here. So I worked towards it, and that's what I got. This looks an awful lot like that. The only difference is I've replaced x by x over 3. So let's write that as 2/3 times a series summing from n equals 1 to infinity, x to the n. Well, instead of our x, I've got x over 3. So x over 3 to the nth power. Cool. So that's our series. That's an infinite power series representation of this function. Now, of course, what you need to answer after that is, when does that converge? Well, remember our criteria. The absolute value of our x, in this case x over 3, has to be less than 1. So probably a couple ways to solve that one. Easy way to work on this would be to just repeat the binomial, or excuse me, not to repeat the binomial, repeat things like this. And then if we multiply both sides by 3, we get -3 is less than x is less than 3. Nice. So what that's saying is that our infinite power series, this infinitely long polynomial, will actually mimic their function as long as the values of x are between -3 and 3. At these endpoints, you're gonna have a tough time getting convergence. So let's take a look at that and see what that means. First things first though, let me kind of recap what we did. We took our function, we wanted to make it look like this function. So I did that in a couple ways. I first of all factored out the numerator, and then I multiplied by 1/3 in the numerator and denominator so that I got a 1 in this position in the denominator. And at that point, the form of this matched the form of this. So my x was really x over 3. I put that into my function. That's your power series for this function. If you solve for when this converges, you can solve like this and see this is going to converge for x in this range. So, converges for these values of x. Let's see what that means graphically. We can do that with Desmos. So let me come over here. Here's our function. You might not be surprised to see a vertical asymptote at x equals 3. That's because at x equals 3, the denominator is 0. That's a problem. Let me dial this down back to 0. So we'll start out summing up just the first term, which is, no, I guess I dial it down to 1. The first two terms of this series give me essentially the tangent line to this function at x equals 0. Okay, so near x equals 0, it's not a bad approximation to this curve, but much beyond that, it's not so good. So what we could do is add more terms. And every time I increase the value of b, I'm adding another term in this series. And watch what happens. Let me zoom in a little bit. Watch what happens to this curve and how close it gets to the red one. Keep in mind the blue one is our approximation. The red one is the actual function. So, all right, so right now, not too bad. Probably use this between, say, -1.5 and almost 1.5. But as we add more terms, watch what happens on the right end. This tail over here is getting it closer and closer to this one as we increase n. Now over on the left, this is going to bounce up and down because you're changing from a negative, from an even degree polynomial to a negative degree polynomial. So it's reflecting that behavior. But even as we do so, that approximation is getting better and better for values of x that are farther and farther away from 0. As we increase our degree of our polynomial, then this approximation gets better and better for a wider value of x's. So we didn't quite get convergence for values of x near -3, but we didn't expect that. Because keep in mind, this only converges for x between -3 and 3. So at the endpoints, we're going to struggle a little bit, but overall, it does a pretty remarkable job. So let me zoom it back to a first degree approximation and keep an eye on just this right side. Watch how this curve just eventually bends up and gets really nice and close to what we have over here. Let's try it in projector mode. That's a little bit better. So you can see as you increase the degree of the polynomial, you're just getting better and better approximations. So we're at n equals 20 right here, and jump up to n equals 25. Of course, you can keep going. I only stopped here because that's where I stopped my animation. Okay, let's do some more here. So we'll do example B. That's going to be f of x is x over 2x squared plus 1. We're going to play the same game we did with the last one. We want to make this look like something of the form 1 over 1 minus x. So that's our goal. To get there, the first thing I'll do is I'll factor out the numerator like I did last time. So that's going to be x times 1 over, well, let's change the order on those terms. 1 plus 2x squared. And we're getting pretty close, except I need a minus here. So can you think what I'm going to do to get a minus there? And give yourself a big pat on the back if you said write it as minus negative 2x squared, like that. And that's indeed what we're going to do. So that's perfect. Now, this part here is in this form. So I can use our power series representation for this function to come up with a power series representation for this one. So it's going to be x times a sum from n equals 0 to infinity of something to the nth power. Can you think what that something is? Instead of our x, we had this. It would be minus 2x squared, like that. You could leave it like this. Not sure exactly what WebAssign would do with that, but I'm going to clean that up a little bit, or at least rearrange it a little bit. I'm not sure it's really cleaning up. N equals 0 to infinity. I've got a negative 1 to the n power, so I'll factor that out. And then a 2 to the n power. And then x to the 2n power. So it's a different way to write that one, and that's fine. What about its radius of convergence? Where is this one going to converge? Good question. Let's take a look at it. It's going to converge when the absolute value of that term is less than 1. Absolute value of this is less than 1. 2x squared. Now, it doesn't matter if I have the negative or not, so we can just get rid of that. In fact, let's do this. Let's write this as the absolute value of negative 2, absolute value of x squared is less than 1. This is just 2. And I can divide on both sides and write x squared is less than 1 over 2. You might be wondering why I lost the absolute value. Well, because x squared is positive, and I don't need the absolute value around that. And even though it's not exactly the right thing to do, I am going to take the square root on both sides. Actually, you know what? Let's do this. This is going to be true when x is between these values, or x squared is between those values. And that's going to mean the value of x is less than the square root of 1/2, which you might know in its other form, root 2 over 2. And no, you can't take the square root of a negative. I'm just going to leave that negative out front and write this. So it's going to converge in this range. Just a quick FYI, that's about 0.707. So again, you've got another series, and it converges for x in between negative root 2 over 2 and root 2 over 2. Okay. Kind of recapping what we did here is the same thing we did in the last one. We factored out the x, rewrote the denominator, changed the order, and then wrote it as negative of negative 2x squared. At that point, this little piece right here is my x. I can plug it in the series this, which I did. I just rewrote it like this. I'd probably appreciate if you did something like that on an exam, but I mean, it's not wrong like that. Do me a favor though, write it like that. Now, one of the amazing things and one of the very, very powerful things about series is you can integrate them and you can differentiate them. And that's what we're going to do next in example C. Find a series for the natural log of 1 plus x. Well, there's two things that you have to note in doing this one. First, note that 1 over 1 plus x is 1 over 1 minus negative x. And again, we can use our series representation for 1 over 1 minus, x, except we're going to plug in negative x here. And that's going to be the sum from n equals 0 to infinity of negative x to the n, or better yet, n equals 0 to infinity, negative 1 to the n, x to the n. So that's the first thing to note. The second thing to note is that ln of 1 plus x is the integral of 1 over 1 plus x. You just integrate that, quick U substitution if you need to, and you're going to get this. Now you might say, well, wait a minute, when you integrate this, you're going to get plus a c, and that's true. But if I wrote this as ln of x plus 1 plus my constant, let's think about what happens when x equals 0. If x equals 0, I end up with the log of 1, which is 0. This is 0, and that's really telling me that c would have to equal 0. So we can get rid of c, and that's kind of nice. So with those two things to note, let's actually calculate a series representation for this. So ln of 1 plus x is going to be the integral of the series for this. Integral of the sum from n equals 0 to infinity of negative 1 to the n, x to the n. Ooh, you should be hollering at me. Yeah, I forgot my dx. My apologies. Now, that dx is important because it reminds you what you're integrating with respect to. We're integrating with respect to x. So anything that's not dependent on x can go out of the integral. Just like when you're integrating, say, 3x squared, 3 can come out in front of the integral because it's independent of your variable. So these can come out of the integral. So it's going to be the sum from n equals 0 to infinity of negative 1 to the n, the integral of x to the n dx. And that looks pretty doable. In fact, that's something you learned in Calc 1. Go ahead, jot down the answer before I write it, or pause the video and do the same. Got it? Again, we're not going to worry about that constant because that constant is going to turn into a 0. Because the log of 1 plus 0 is going to be 0. So my constant has to be 0. So yay, there's my answer. Now, a neat thing about integrating is that the radius of convergence is still going to be the same. So radius of convergence is still r equals 1. Okay, now if you're looking at the interval for convergence, the interval for convergence, -1 is less than x, less than 1. You'd have to plug in and test each endpoint. And in this case, I believe this is going to converge at n equal 1 because you're going to get an alternating series, but not at n equal -1. No, because your series is not going to alternate. If you spend a little time with the algebra, you'll always end up with a negative number in the numerator. So actually a -1. So this would be your interval of convergence. Nice, but really cool that you can integrate these series, and very powerful. You're going to see a lot of series solutions when you take differential equations, and it's just nice because series are made up of polynomials, and polynomials have lots of wonderful friendly properties. So, looking okay there?
I found this on the web.
Siri's interrupting me. Sorry about that. Siri found something on the web. I hope that it's useful. Does Siri know how to integrate like this? No, Siri's silent. Okay, let's do another example. And then we'll kind of take a small detour break from this and look at something else. Example D. Find a series for tangent inverse of x, which is also arctan of x. Remember, those are two different notations for the same thing, just like the square root of x or x to the 1/2 power. Well, let's do this. Let's recall that the arctan is the integral of 1 over 1 plus x squared dx. Fair enough. And I can write that as 1 over 1 minus negative x squared. And I still have a dx here. This puts it into the form of a series. So, okay, let's rewrite that as the sum from n equals 0 to infinity of negative x squared to the nth power, like that. And I still have my dx here. I'm going to clean this up before I integrate. It's going to be helpful because I can get rid of a few things. So that'll be the integral of the sum from n equals 0 to infinity. I'll have a -1 to the nth power. And then that'll leave me with x to the 2n dx. Now, look at this integral and ask yourself, what part of it depends on x, your variable of integration? And if you spotted this term right here, bonus points for you. So what that means is I'm going to move this integral sign in here and ignore this other stuff because it's really a constant and a sum, and the properties of an integral allow us to interchange these operations. So that's going to be the sum from n equals 0 to infinity of -1 to the n times the integral of x to the 2n dx. Well, that's not too bad. That's actually pretty good. So none of this stuff has changed. -1 to the n. Integrating that means adding 1 to the exponent and dividing by the same exponent. Wow. That's pretty cool. And that's going to converge. It's going to have the same radius of convergence that our geometric series does. So, nice. Converges. How's that one looking? Looking okay there? Cool. All right. I said we're going to take a little change of path or detour. I think I want to do one more example before we take that detour. Yeah. Is there anything else I want to say here? Is there anything else you want me to say here? You want me to say that you don't have to know this? Well, you don't have to know this. All right, I'm kidding. You knew that was coming. Okay. Let's try example E. Then we'll do a little detour into changing the index of summation. So, example E. We want a series for f of x equals 2x plus 3 over x squared plus 3x plus 2. Now, what you're going to need to do is realize that the denominator factors 2x plus 3 over x plus 1 times x plus 2. And do a partial fraction decomposition. Now, if you don't need to see this, you can fast forward to the happy ending. That's fine. If you were to multiply both sides of this by the LCD, and the LCD is just this denominator, x plus 1 times x plus 2, what you'll end up with is 2x plus 3 equals a times x plus 2 plus b times x plus 1. And then what I would do is, first of all, set x equal -2. If x is -2, then what I end up with is -2 times 2 is -4. -4 plus 3 is -1. So -1 would equal a times 0 plus b times -1. Right, because -2 plus 1, that gives me -1 equals -b, or b equals 1. Cool. Now what? Now let's set x equal to -1. If I set x equal to -1, then I end up with -2 plus 3 is 1 equals a times -1 plus 2 is 1 plus b times 0. And that tells me that a equals 1. So I can rewrite this equation up here, excuse me, this function up here as a sum of partial fractions. So let's see what that looks like. That's going to be f of x equals a, which is 1 over x plus 1, plus b, which is also 1 over 1 plus, actually 2 plus x. So this one is not quite in the right form. Actually, neither of those is quite in the right form that we need. So let's rewrite those. So it's going to be 1 over 1 minus negative x plus 1/2 over 1 minus negative x over 2. And I guess I probably should, for the benefit of the viewer, fill in a little detail here. To make this a 1, I'm going to multiply by 1/2 over 1/2. And that puts the 1/2 in the numerator. And then I get the 1 in the denominator like I want. So you end up with 1 plus x over 2, which you rewrite like that. Both of these are nice series. I'm going to take the 1/2 out in front. So that's going to be the sum from n equals 0 to infinity of negative x to the n, plus the 1/2 is going to come out in front, and I'll just put that in front of the series, sum from n equals 0 to infinity of negative x over 2 to the n. These negatives, we tend to factor them out, so let me do that. N equals 0 to infinity, negative 1 to the n, x to the n, plus 1/2, sum from n equals 0 to infinity, negative 1 to the n, x over 2 to the nth. And you could write it as x to the n over 2 to the n. That's not a bad way to write it. Just happened not to in this case. So not so bad once we got the factorization. We do have a little bit of a question to answer here. This is going to converge as long as the absolute value is less than 1, absolute value of x. This is going to converge if the absolute value of x over 2 is less than 1. And since 2 is already positive, you take it out of the absolute value of x over 2 is less than 1, or absolute value of x is less than 2. So I get 2 different intervals of convergence. Which one's right? Do I add them? Get absolute value of x less than 3? Don't know. So tell you what, let's investigate that with our eyeballs. Let me shut off some of these older graphs and move down to here. So here's your function. You can see you've got vertical asymptotes at -2 and -1, as you would imagine. And what I did was I created a function for each series and then added those two together to get the final function. So let's see what happens as I increase the values here for C. And let's see. No pun. All right. Let's move that down here. I guess that'll work. Let's increase the values for C and see what happens. Now the question we have to answer is my interval of convergence between -1 and 1 or between -2 and 2? I don't know about you, but I'm not seeing that the green function approximates the red one outside the interval -1 to 1. In fact, that's the case. So whenever you're confronted with the sum of the two series like this, you always take the smaller radius of convergence as being the radius of convergence for the whole thing. So choose the smaller radius of convergence. There, looking good. Okay, I promised you a break of sorts, right? So we're gonna slow down on this stuff for just a minute to talk about a little trick that's gonna help you out in your later classes and in this class as well. I've seen WebAssign use it in some of their answers. I'm not sure if they require it of your answer, but if they do, you'll be well prepared here. So let's take a look at this series. The sum from, let's call it n equals 0 to infinity of 1 over n plus 1 squared. Something like that. Now, if I ask you for the convergence or divergence of this series, certainly your intuition would say, well, look, we get a squared term, it probably converges. Yay, that's great. But you couldn't exactly apply the p-test because this is not a p-series. You have n plus 1 squared, not n squared. But here's what you can do. Let's suppose we wanted just like an n squared here, except now n has already been used. So let me use a different variable. Let's call it k. So let k equal n plus 1. What I'm going to do is I'm going to rewrite my series. Sum from k equals, and I'll have to figure out what it equals, but k is going to be n plus 1. So I'm going to have 1 over k squared. Now if k equals n plus 1, let's figure out something. At n equals 0, 0 plus 1, okay. That's going to mean k equals 1. Okay. So at n equals 0, which is where this series starts its summation, 0 plus 1 is 1. So k is going to start at 1. It's going to go all the way up to infinity, right? Because infinity plus 1 is still infinity. And so I got a new series. And there's two great things about this. First of all, this is now a p-series. And you can say, oh, well, that converges. It's a p-series with p equal 2. So that's really nice. The second thing is that this actually was calculated. The exact sum of the series was calculated by my favorite mathematician, Leonard Euler, Swiss mathematician, remarkable, talented. The sum of that is pi squared over 6. So a couple nice things come out of changing the variables there. Now, let's do this in more of an applied situation. For example, let's see, change the index of summation on this series. The sum from n equals 1 to, actually, you know what? Hang on here. 1 or 0. We'll start out with a 0. You don't have to copy it down. If you already got a 1 there, just leave it. And I'll tell you when to pick up your writing again. So the sum from n equals 0 to infinity of negative 1 over 4 to the n plus 1 power times n times x to the n minus 1. All right. Now I said, you know, if you had a 1 there, that's fine. Just leave it as a 1. Because I want to point out something about this. If you think about this series and you start plugging in the different values, n equals 0, n equals 1, n equals 2, what's going to happen at n equals 0? What's my first term going to be in this summation? If you said 0, triple bonus points for you. Because at n equals 0, this all disappears. So if plugging in a 0 doesn't contribute anything, I could just as well start my series at 1. So we'll do that. Negative 1/4, n plus 1, n times x to the n minus 1. Now, for a variety of reasons, one of which we just saw up above, sometimes you want to start a series at a different place. You want to start at summing at 0. Okay, we can do that. We're going to rewrite this so that this series starts at 0. So what's that going to mean? Well, let's come up with a different index of summation then. Let's let I equal, let's choose n minus 1, because that makes our index here, excuse me, not our index, but our exponent a little bit nicer. It's not really an aesthetic reason that I'm changing the variables. It's just practice. So if I let I equal n minus 1, then I'll just have a nice x to the I term there. That'll be nice. With that, that means equivalently that I plus 1 equals n. Nice. And that when n equals 1, at n equals 1, what do we get? At n equals 1, I equals 0. I equals 0. So with this substitution right here, I can rewrite this series equivalently, but starting at a summation of I equals 0 as opposed to n equal 1. And can I say that there's a lot of gains here? Not particularly in this problem, but that's okay. Sum from I equals 0 to infinity, negative 1/4 to the n plus 1, n plus 1, x to the n minus 1. Remember, everywhere that I have an n, I'm going to replace that with I plus 1. So how's that going to look? Well, it's going to be I plus 1, and then I plus 1, and I plus 1. So to clean that up, that'd be I equals 0 to infinity, negative 1/4 to the I plus 2, and I plus 1 times x to the plus 1 and minus 1 cancel, x to the I. There you go. That's an equivalent series to what I have up above. Now, if you want some more practice in something like this, what you could do is do this last example for yourself. And that would be negative 1/2 the summation from I equals, well, we'll start out with 0 to infinity of negative 1 to the I power over 4 to the I plus 2 power times I plus 1 times I times x to the I minus 1. Now, if you look at this, you might notice that at I equals 0, this term disappears. So you might as well start the series at I equals 1. But then, for whatever reason, you decide, you know what? I want to start this series at I equals 0 or something equals 0. So we can make a little substitution. And if you make this substitution, you can rewrite your equation like this. If you want to, hit the pause button and try and quiz yourself. K equals 0 to infinity, negative 1 to the k plus 1 over 4 to the k plus 3 times k plus 2 times k plus 1 times x to the k. So again, just another change of notation there for you. All right, probably not the kind of little break you were hoping for. Sorry, I don't have a lot prepared on Euler. I couldn't, I guess I could talk about it a little bit. What was amazing is that as much work as he did, he was blind the last 17 years of his life. And yet they were still publishing his work 50 years after he died. So amazing mathematician. Spent a lot of his working career in Russia, even though he was born in Switzerland. Okay, back to working with our series here. And we're on to example F. You know, as you study, it's good just to give yourself time on and time off. So at this point, maybe it's not a bad idea to take a quick break for yourself, take a little stretch away, walk away, try and let this stuff sink in a little bit. You know, and then on your way back, try and solve one of the problems that we've looked at in your head. Those are good studying skills to try and resolve things in your head without looking at your book. So good study skills. You can check out a video by Barbara Oakley, a professor at Oakland University, talks about having a mind for numbers. And she came from humble beginnings to be a professor. But she didn't like math for a long time. Okay, trying to find. Okay, example F. We're going to do several things here. We're going to, first of all, find a series for 1 over 4 plus x squared using differentiation. Once we have that, we're going to find a series for 1 over 4 plus x cubed using differentiation. And finally, find a series for x squared over 4 plus x cubed. Okay, so lots going on here. Let's start with the first part, find a series for this using differentiation. Now, okay, so that one's a little bit tricky. If we wanted to call it f of x is going to be the derivative of some function. So what do I differentiate to get this? Well, an equivalent way to answer that would be to do the opposite. I could integrate my function and see what I get, and then when I differentiate it, I'll get the integrand. So I'm going to take and integrate 1 over 4 plus x squared dx. Now, you might think of a u substitution here. U equals 4 plus x. But here's the thing. If you thought of a u substitution, you'd find that du equals dx. And if that's the case, you can kind of do these things in your head as if it was just 1 over u squared. 1 over u squared integrates to u to the negative first power divided by negative 1. Or in this case, 4 plus x to the negative first power divided by negative 1. Plus a constant, let me rewrite that, negative 1 over 4 plus x plus our constant. Now because we're going to be differentiating this and the constant is going to go to 0 when we differentiate it, I'm going to leave the constant out. I'm going to set it equal to 0. Bottom line, though, is now I can look at this and say, okay, if I differentiate this, I'll get this. That's what I needed. So 1 over 4 plus x squared is the derivative of negative 1 over 4 plus x. So I did a lot of work to figure that out. Now, if you look at the answer on WebAssign, they'll say, oh, well, observe this. All right, I filled in a lot of detail here for you, but let's work with this. This is not too far away from a series that we know and love, d by dx. Call it negative 1 times 1 over, let's see, 4 plus x. You might look at this and say, all right, I know where you're going, parent. We need a 1 here. So I'll multiply by 1/4 over 1/4. So it's going to be d by dx, negative 1, 1/4 over 1 plus x over 4. Two last things. Let's take this, put it out in front. 1/4 times negative 1, negative 1/4 over 1 plus 1 minus negative x over 4. Beautiful. Whew. Stretch, take a nice breath, because we worked hard to get here. But we can figure things out from here. That is, if Windows Defender will leave me alone. Okay. This part right in here, we can replace with a series. So derivative, the negative 1/4 can come out. That's a constant. Negative 1/4 times d by dx. The sum from n equals 0 to infinity of negative x over 4 to the nth power, like that. And now I can interchange these two operations, summation and the derivative. There's only one thing stopping me, and that is I'm running out of room. So okay, so it's going to be negative 1/4 times the sum from n equals 0 to infinity of the derivative of, let's see, let's clean this up a little bit first maybe. Negative 1/4 d by dx, the sum from n equals 0 to infinity of negative 1 to the n, x to the n, over 4 to the n. And what's helpful about that is these terms are constant with respect to the variable. So negative 1/4 to the n, I can kind of ignore that with my derivative. I'll get x to the n. I apologize, I recombined those, my bad. But the derivative of x to the n is just going to be n times x to the n minus 1. This part is invisible because it's a constant. It's not a variable with respect to x. It's just a constant. So this becomes negative 1/4 sum from n equals 0 to infinity of negative 1/4 to the n times n times x to the n minus 1. You might notice that at n equals 0, that first term disappears, and that's okay. The good news is that we've already worked with this. All right, we played with that, and we wrote it. You can multiply this in and have a 4 to the n plus 1 term, and this would be -1 to the n plus 1 term. So we can put that back in here and play around with it a little bit and eventually end up with the sum from n equals 0 to infinity. Like I said, I'm going to bring this back in. That's going to increase this exponent by 1 of -1/4 to the n plus 1, n times x to the n minus 1. And by playing around with our exponents or our index of summation like we did earlier, we can end up with this series. Sum from k equals 0 to infinity of -1 to the k power over 4 to the k plus 2 power times k plus 1 times x to the k power. But this part we've already done. I'm not sure if we use the same variables, but we already did that. Okay. Don't know about you, but I'm running out of gas on this stuff. So about 3 more examples to go. One more part, actually 2 more parts in F, and then GH, maybe I. Keep in mind, there's 3 types of mathematicians in this world: those who can count and those who can't. Okay. All right. Let's continue. Find a series for this. I'm going to try and speed this one up a little bit. If you integrate that to figure out what you're going to differentiate, then what you'll end up with is the integral from the integral of 1 over 4 plus x cubed dx. It's going to be -1/2 times 1 over 4 plus x squared. And we've got a series for that. So we're going to take advantage of that and try and come up with a series solution or come up with a series for this by differentiating this series. So 1 over 4 plus x cubed is the derivative of -1/2 times 1 over 4 plus x squared. We just came up with a series for that. So let's plug in the series here. That's going to be d by dx of -1/2 of the sum from k equals 0 to infinity of -1 to the k over 4 k plus 2 k plus 1 times x to the k. The good news, if you're looking at this and going, oh my God, how am I going to differentiate that? The good news is that there's really only one term you got to pay attention to, and it's right here, because we're differentiating with respect to x. So we can move the derivative all the way here. It's like being Monopoly, right? Fast forward token to go. That's where we're going to go, right there. So that's going to be -1/2 times the sum from k equals 0 to infinity, -1 to the k over 4 to the k plus 2, k plus 1 times the derivative of x to the k. So d by dx of that x to the k. So the derivative passed all the way to there. So any volunteers to differentiate that one for me? Yes, you in the back. Perfect, thank you. Derivative there is just going to be k times x to the k minus 1. K plus 1 times k times x to the k minus 1. And we played around with one just like this earlier, and you can relabel this to have a different index of summation and end up with this series, 1/2 the sum from, let's do I equals 0 to infinity of -1 to the I power over 4 to the I plus 3 power times I plus 2 times I plus 1 times x to the I power. Wow. Give yourself a pat on the back if you're still hanging with me on this one. You're doing well. At least the last one's going to be a little bit less challenging than you might think. The last one, we want to find an expression for f of x equals x squared over 4 plus x cubed. Well, the thing to notice here is that that's really x squared times 1 over 4 plus x cubed. And we've got a series for that. In fact, that series for that is right up here. So if I multiply it in an x squared, I'm just going to be adding 2 to that exponent. So the overall series, and I hope I have enough room for this, sum from I equals 0 to infinity of -1 to the I over 4 to the I plus 3 times I plus 2 times I plus 1 times x to the I plus 2 power. Just barely enough room there. So sorry I squeezed it in. Once again, 1/2 the sum from 0 to infinity of -1 to the I power over 4 to the I plus 3 power times I plus 2 times I plus 1 times x to the I plus 2 power. Brilliant. If you haven't already taken a break, give yourself one, because we got a couple more problems to do. They actually work out pretty amazing. I'm really happy with the way they worked out. Oh, that last one. Let me put that back up here. Should have done something after that one.
That was easy.
Yes, beautiful. Not too many times in this class I can use that button. Okay, example G. And this next one is going to be a little bit easier than our last several. So if your mind is going numb, at least you got one that isn't quite as intense. Sample G. Ooh, that's an accent. I like that. Using a sigma as opposed to an E. Find a series for x to the 4th arctan of x cubed. Well, in case you shut off the video for a while and walked away and lost your place a little bit, let me remind you that earlier we derived this series for the arctan. Sum from n equals 0 to infinity, -1 to the nth power times x to the 2n plus 1 over 2n plus 1. Well, but I need the inverse tangent of x cubed. Tangent inverse of x cubed. Well, that just means that wherever there is an x, I'm going to put in x cubed. So let's do that here, x cubed and x cubed. And this can simplify. This exponent multiplies this exponent, so there'll be the sum from n equals 0 to infinity, -1 to the n, x to the 6n plus 3 power over 2n plus 1. And we're getting closer. What else do we need? We need to multiply that series by x to the 4th. So x to the 4th tangent inverse of x cubed is going to be x to the 4th times all of this, sum from n equals 0 to infinity of -1 to the n, x to the 6n plus 3 over 2n plus 1. This can just come into the summation and directly multiply this. When you multiply things with the same base, you add their exponents. -1 to the n, x to the 6n plus, well, 4 plus 3 is 7. Beautiful. Where does this converge? Well, it converges same place that series converged, which was when absolute value of x is less than 1. So now we want the absolute value of x cubed less than 1. And that's going to be equivalent to, I mean, x cubed less than 1 means exactly x as less than 1 in absolute value. They're going to have the same radius of convergence that it did before. Converges. Okay. Let's give your instructor a break here. Let's do another one, except this one is just going to be a narration on my part. Suppose you're asked to find a power series for something like this. Natural log of 1 plus x over 1 minus x. Now, hopefully one of the things you remember is that there's some properties of logarithms that you can use. So recall natural log of a over b is a natural log of a minus a natural log of b. And we've got a series for each of our logs that are going to result from this. We've got a series for 1 plus, or log of 1 plus x over 1 minus x. So let's just narrate this. You're going to use your properties of logs to break up that series or break up that expression into 2 expressions, into this one and this one. And then these are the result of integrating this function and this function. And those can get rewritten here and here so that now we can plug in some series. And we're going to combine these two back into one integral. So this here, just integrate once and replace each of these with their series. So that's done over here. Now, when you integrate those series, the first one is going to give you an alternating series like this. The second one's going to be always positive. And here's kind of the nice magic in all this. If you take a look, that x and that x can cancel. And not the even ones, but the odd ones cancel. So what you're left with, the one here and the one here, they add up. The x squared and the x squared, they add up. So I get 2x squared and 2x to the fourth. And basically 2x to the 2n right over here. So if you work with just a series, you can come up with this. And now we integrate by adding 1 to the exponent and dividing by the same exponent. So that's this part right here. And then here. You might be wondering, well, what about that constant? The constant is 0, because if you plug in x equal 1, you'll end up with the log of 1, which is 0. So that means c has to be 0. So there's your function. There it is, right there. F of x is the series. It's going to have a radius of convergence of 1. And if you look at the endpoints, you'll see that you don't get convergence at either endpoint. So you can check at x equal 1 and x equal -1 and find out that it doesn't converge. So there you go. Okay, so I saved my hands from writing for one last problem. If you're still with me, pause the video, do a victory lap around the room, and come back for the last one. This last one, I gotta tell you, I really like these kinds of problems, and you can probably expect to see one like this from me on an exam and or on a final exam. It's just amazing. So suppose, and let's see, this is example I, if I'm keeping up with things. The last one is example H. Suppose you had to find the integral from 0 to 0.3 of x to the 6 over 1 plus x to the 5th dx. Now maybe if you're clever, you can figure out some way to directly integrate this. But keep in mind, we don't need to directly integrate this if all we want is a good approximation to this. We're going to approximate to within 6 decimals digits. And let's see how we'll do that. Well, by now I hope you're getting used to the trick. That is, we're going to play around with this and replace this expression with a series. And then we'll be able to integrate the series, and then we'll have to go from there. But for starters, 0 to 0.3, I'll write that as x to the 6, 1 over 1 minus negative x to the 5th dx. I did a lot there, so let me kind of let you catch up for a second. I brought the x to the 6 out in front. I changed the denominator to minus a negative. Why did I do all that? Exactly. It's because I'm going to replace this by a series. 0 to 0.3, x to the 6, the sum from n equals 0 to infinity of negative x to the 5th raised to the nth power. Negative x to the 5th raised to the nth, and then I still have my dx here. Now, it might be convenient to clean this up a little bit. I'm going to do so. So that'll be the sum, excuse me, the integral from 0 to 0.3 of x to the 6 times the sum from n equals 0 to infinity, negative 1 to the nth power, and then x to the 5 times n dx. And now that I cleaned it up a little bit like that, Now I can bring in the x to the 6th. And when I multiply things with the same base, I'm going to add the exponents. So this becomes x to the 5n plus 6. So it's going to be the sum from n equals 0 to infinity, -1, x to the 5n plus 6 dx. Now I can finally gain some ground on this. I can interchange these operations. That should be an n here. I can integrate this function of x. This other stuff stays out in front. Sum from n equals 0 to infinity of -1 to the n times the integral from 0 to, let me call it 3/10 of x to the 5n plus 6 dx. Now, to integrate this, I'm going to add 1 to the exponent and divide by the same exponents. So that's going to be x to 5n plus 7. So adding 1 to the exponent, divide by the same exponent, and that has to get evaluated between 0 and 3/10. Now I might be showing you a little bit more work than I need to. That's okay. This is going to be the sum from n equals 0 to infinity of -1 to the n, 1 over 5n plus 7. That's a constant. I need to plug in values of 0 and 3/10 into this expression. So I'm going to have 3/10 to the 5n plus 7 minus 0 to the 5n plus 7. Now we can clean up this expression. I'll just write that as 3 to the 5n plus 7 in the numerator and 10 to the 5n plus 7 in the denominator. And I get an expression like this. -1 to the n, 3 to the 5n plus 7 over 5n plus 7 times 10 to the 5n plus 7. So that's the exact value of this integral. But if you want to approximate it, notice that the terms are alternating. So what we have to do is we have to figure out, well, how far out, how many terms of n do I need before this is less than 0.000001, which would be our approximation to within 6 digits. So something less than 1 times 10 to the -6th. So less than 10 to the -6. Okay. Probably the easiest thing to do rather than try and solve for that is just do it by trial and error. Let me do it up here on this. So I'll clear out some old stuff here. And let's, no, wrong mode. Not that the mode would have really mattered in this case. Clear that. Let's clear out my key history as well. And let's type in some functions. So 3 raised to the parentheses 5x, using x as opposed to n, 5x plus 7. And then you got to exit the exponent, so there'd be a right arrow, divided by, you need 2 parentheses, 2 left parentheses, because the first one we're going to put in 5x plus 7, close off that parenthesis. And the next one, I need my 10 raised to the 5x plus 7, 5x plus 7. Okay, looks pretty good. Now let's go to our table. So I'll hit second and then table. These values here, I'll clear them out. Let's just for giggles type in a 0. And a 0, man, look at that. You're already getting 4 digits of accuracy at x equals 0, at x equals 1. Wow. So if you just use the first 2 terms, even the first 1 term, you're getting a really, really accurate polynomial. That's just amazing. So yeah, with just 1 term, the very first term gives you accuracy to within 6 digits, because the next term that you would use, leave off, your error is going to be less than this term. If you just use the first term, wow, you're getting an amazingly accurate answer. So I don't feel like typing all that stuff in and plugging in an x equals 0. So I'm going to cheat. This is a Jeff Parent internet only special. If we hit the vars key and then go over to yvars, let's press enter and then enter again. We want this function evaluated at 0. So let's put parenthesis, 0, parenthesis. Yay. That's our approximation. How does that compare to if we just did it this way? Math 9, integral from 0 to 0.3 of, let's do a nice fraction, x to the 6th divided by 1 plus x to the 5th. And then dx. How close do we come? Pretty close. Really close. If you wanted to use just 2 terms, let's go back here a couple times. No, one more. There we go. And add in the second term. So if you want to see the trick again, you hit the vars key, right to yvars, press enter again. This time we want this evaluated at 1. So if we add up the first 2 terms, wow, we're getting a nice answer there. Pretty close. Okay, that'll do it for this, this section. Hope you follow along, and bonus points to you that are still here. Go Euler. See ya.